Halo everyone, Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Peace and blessing be upon us all. Respect to all goodness and salam harmony. Welcome to my video presentation. The topic that we are going to shortly discuss today is titled IP addresses. Before we dive deeper into the core concept, please let me introduce myself. My name is Putudia Krisna Pranimutami with student ID number 2511021030. I'm a student majoring in Educational Technology at Ganesha Universities of Education. On this wonderful occasion, I am absolutely thrilled to share some insight regarding this topic, which serves as one of the most fundamental pillars in the world of computer networking and the internet. Now, before we look at the detailed presentation slides, I would like to show you a mind map about IP addresses that I have designed beforehand. Through this conceptual map, our entire material today will flow in highly structured manner. We are going to learn everything starting from its basic format, the generational differences, the class divisions, its restricted addresses, all the way to smart network management strategies using the subnetting method. So, please make sure to watch this discussion from the very beginning to the end. Let's jump straight into the first point. Let's move on to our very first topic, the definition of an IP address. What exactly is an IP address? By definition, an Internet Protocol address or IP address is a unique identity assigned to its computer or host in a network to enable communication. Just like our physical home addresses, without this unique number, devices will not know where to send or receive data packets and communication will be impossible. Now, who coordinate and distribute these numbers globally so they never conflict? The international regulating body responsible for this is called IANA, which stands for the Internet Assigned Numbers Authority. Technically, the version we encounter most frequently in our daily lives is IPv4. IPv4 is composed of a 32-bit binary structure. However, because humans would find it incredible exciting to read a long string of ones and zeros, this binary structure is converted and written in a decimal format divided into 4 octets. A classic example that we see all the time is 192.168.1.1. Inside every single IP address, the structure is always split into two essential parts. First is the network ID, which identifies the specific network or X like the street name. Second is the host ID, which identifies the specific device or X like the host number. Moving forward, let's explore the technological evolution between two generations, IPv4 versus IPv6. Why do we even need a new version? The core reason is a massive population explosion of digital devices. As I mentioned earlier, IPv4 uses a 32-bit structure, which mathematically limits its capacity to around 4.2 billion addresses worldwide. Today, a single person can own multiple devices, which means IPv4 addresses are officially running out to rescue the internet. Experts developed IPv6, which provides a massive address space using a 128-bit structure. This creates an astronomical number of addresses. Beyond capacity, IPv6 offers incredible future-proof features. It offers more efficient routing for a smoother connectivity experience. In terms of security, IPsec is a mandatory standard requirement in IPv6. Lastly, configuration is a breeze because IPv6 natively supports automatic configuration, meaning devices can seamlessly generate their own addresses the moment they connect. To organize network distribution systematically, Ayana divided the IPv4 space into specific classes based on operational scale. Let's break down these classes one by one. First, we have class A, spanning a range from 1 to 126 in the first octet. Class A is designed for a large-scale networks because a single network can accommodate over 16 million host devices. Second is a Class B with a range from 128 to 191. This class is tailored for medium-scale networks, making it the perfect fit for large university campus or corporate headquarters. Third is a Class C, covering the range from 192 to 223. This is the most common class we interact with daily, supporting a maximum of 254 computers per network. The Wi-Fi router at your home almost constantly utilizes Class C addresses. Finally, we have Class D and Class E, ranging from 224 to 255. Class D is strictly reserved for multicast delivery like Zoom video conferences. Class E, on the other hand, is kept strictly for experimental and research purposes by scientists and network engineers. Now, please pay close attention to this section. In IPv4, certain IP addresses are restricted and cannot be assigned to regular host devices like your personal laptop. The network address. This is any IP where the host bits end in 0. It serves strictly as the network identity. The broadcast address. This is the IP that ends in 255. It is reserved for mass delivery, meaning individual computers are banned from claiming it. The loopback address. This is the famous 127.0.0.1. It is used strictly for self-testing purposes on the local computer. Private IP. These are specific blocks of addresses reserved exclusively for internal local networks, and they are strictly banned for the public internet unless they use a translator gateway. To truly master networking, we must understand how to bridge the communication gap between humans and machines. As you can see from the illustration on the slide, robot natively process binary digits ones and zero, while humans naturally use decimals. Number conversation is our ultimate translator. Let's look at how these conversations work mathematically. To convert decimal to binary, we take our decimal number and divide it by 2 repeatedly. We carefully record the reminders and then we read those reminders from the bottom all the way to the top. To convert binary to decimal, we utilize a positional with value table based on powers of 2. We simply sum up the values from the table wherever the binary digit is equal to 1. Finally, we arrive at our big topic, Introduction to Subnetting. Subnetting is the practice of breaking down a large network into smaller, manageable subnetworks to improve efficiency and security. The tool that draws these boundaries is the subnet mask. To see this in action, let's look at our case study featuring PTXYZ. This company needs to divide their network systematically to accommodate 5 different departments. First, subnet 1 for HRD, ranging from .1 to .3, 0. Second, subnet 2 for finance, ranging from .3, 3 to .62. Third, subnet 3 for IT, ranging from .6, 5 to .9, 4. Fourth, subnet 4 for marketing, ranging from .9, 7 to .126. And fifth, subnet 5 for operations, ranging from .129 to .158. Thanks to subnetting, PTXYZ now enjoys lightning-fast network performance, zero-wasted IP addresses, and water-like data privacy between departments. Before I wrap up, I just want to share a quick reflection on this material. Honestly, at first looking at all these numbers, binary codes and subnets felt a bit scary and confusing for me. But after breaking it down using the mind map and looking at how it actually works in real life, like in the PTXYZ case study, it all finally clicked. I realized that IP addresses are not just about boring math, it's actually a really cool and organized system that runs the entire internet. Learning this has definitely made me feel more confident about how networks work, and I am really glad I got to study it. In conclusion, after reflecting on this journey, we can clearly see that IP addressing and subnetting are not just abstract mathematical concepts. They are the vital architectural blueprints that keep our global digital society structure secure and running at incredible speeds. That concludes my presentation on the fundamentals of IP addresses and network design today. I sincerely apologize if there were any mistakes or shortcomings during my delivery. Thank you so much for your time, your kind attention, and for watching this video. I close this presentation with Paramasanti. Om Santi 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 Om. Bye.